In this video, we're going to look at the difference between a strong versus a weak acid and also a strong versus a weak base. In the previous video, we saw the definition of a strong acid was 100% dissociation. And so hydrochloric acid is a strong acid. It's actually starts out as a covalent compound, very polar. Remember, chlorine is over here in group number 7. So chlorine and anything in this column would like to steal an extra electron to look like a noble gas. Hydrogen only has one valence electron, and hydrogen, its electronegativity value is pretty small compared to these guys over here. So chlorine pulls hydrogen's electron toward itself, and what happens when this is dissolved in water, then this bond breaks right here. So this, we would say that's what dissociation is, or that's basically the bond is breaking, and the hydrogen's electron now goes with chlorine. So hydrogen without its electron, remember, is simply a proton, and then chlorine now has 8 electrons around it. It's very happy, but this is considered a strong acid because this reaction proceeds all the way to the right. That means there is no equilibrium set up and there is no reverse reaction. This is going to be very significant as we process through the next couple of chapters. What this means is that the chloride ion does not react with water. So any salt that's got chloride in it, we're going to see that the chloride itself will not affect the pH. This does not react with H2O to form HCl. So there's no way that this reaction is going to run in reverse. Chloride is basically just a spectator ion. This also means, more importantly, that 6 molar HCl means we have 6 molar H+. If you recall doing a pH calculation in an introductory chemistry class, the pH depends on the concentration of H+. So it's going to be very easy to do a pH calculation as long as we realize that we have a strong acid. It's a good idea to probably memorize the strong acids. So column 7, those ions here, chloride, bromide, and iodide form strong acids. And we're going to see that fluoride with hydrogen is a weak acid. And that's because that's a stronger bond. When hydrogen bonds to fluoride, because fluoride's smaller, it's just a better fit. But it's a good idea to memorize the strong acids. So chloride, bromide, iodide are strong acids. And also it's not a bad idea to recognize the polyatomic ions. So sulfate and nitrate, I don't have perchlorate on here, but ClO4 minus 1, perchlorate ion. Whenever hydrogen is with these, then that's also a strong acid. We're going to see phosphoric acid, and that's going to be on an equilibrium table. So that's another way to tell if the acid is strong, is we will not find an equilibrium constant for it. But HCl, HBr, HI, those are strong acids, as is nitric acid, sulfuric acid, and perchloric acid. There's probably some more that I can't think of right now. But anyway, all of these are strong acids. So the definition of a strong acid is that this reaction goes all the way to the right, and 100% of the hydrogen ions are pulled off of that molecule. Sulfuric acid is a diprotic acid, so its first, I'm going to go ahead and write that, H2SO4, this reaction would go all the way to the right, and that first hydrogen would come off. We'd be left with the hydrogen sulfide ion, which would be a -1 charge, and the H+. Again, this is what makes the solution acidic. And then the hydrogen sulfate, this could also lose another proton, but that reaction actually runs in reverse. So this is a unique situation here because this could have a conjugate acid or a conjugate base. So that's something we're going to talk about when we look at buffers. So this is the reaction that goes all the way to the right. So the equilibrium constant for that would be infinity. Because this reaction runs in reverse, then we would have some equilibrium constant for that. And we're going to see that in a table. And I've got a picture of this right here showing that hydrochloric acid, and I just put a number here. So strong acid, according to a nice picture, 4 HCl molecules, when we put those in water, are going to break apart into 4 H pluses. So if we have a weak acid, for example, like hydrogen or hydrofluoric acid, so I probably should have said here this was strong. Strong acid, 100% dissociation. This reaction goes all the way to the right. That means chloride is never going to pull a proton off of water and make intact HCl. So a weak acid, that's a different story. A very common weak acid is hydrofluoric. And this is also very electronegative. Remember, this is capable of hydrogen bonding because this is extremely polar. Hydrogen's electron is way over here by the fluorine. Anyway, this reaction runs in reverse. In fact, if I showed that, this really doesn't go very far to the right, and it proceeds much more so to the left. So we're left behind with some H plus and some F minus. And the equilibrium constant for this, if we compare that to here, this does have a reverse reaction. Let me zoom out a little bit here. So this reaction runs in reverse. So the reverse reaction is dominates, really. So this does experience equilibrium. So the equilibrium constant K is quite small. So the K for this is it's acetic acid, 6.4 times 10 to the negative 4th. It might be a 6.8. Should have looked that up first. But anyway, this is a pretty small number. So this is 0.00068. And if you remember from equilibrium, the chapter that we talked about, if K is much smaller than 1, that means the reaction prefers to run in the opposite direction. So this molecule stays intact, and I'm going to be using that term quite a bit. This means, there's several important things here. This means the fluoride ion will react with water and make the intact hydrogen fluoride molecule. So this will end up acting like a base because it'll pluck a proton off of water. That's for a little bit later. So that's going to be very significant in our pH discussion. More importantly, this means, for example, 6 molar HF is not equal to well, I shouldn't say that, 6 molar HF, we don't know what the concentration of H plus is until we work with the equilibrium constant. So this value here is going to be less than 6 molar. So recall when we write an equilibrium expression, K is always products over reactants. So in this case, K is going to equal the concentration of H plus times the concentration of fluoride all over the concentration of the initial acid that we have. So the reactants go in the denominator and the products go in the numerator. So here we'll end up having to solve for H plus. So that's not really difficult to do, but it's going to be a little bit more difficult to calculate pH because we have to look up the equilibrium constant in a table and solve for the H plus concentration. So we're not going to have this case here. This makes the math much easier. If we have a strong acid, we automatically know the concentration of the H plus ion. Where for a weak acid, because this stays intact, we have to do a calculation. That also means that whenever fluoride is in a salt, the fluoride ion is going to affect the pH. So if we just look at a picture of HCl in solution, so this shows what we just talked about, and I put a 4 here because there are 4 H plus ions in solution. So if we have 4 moles of HCl, then we're going to have 4 moles of H plus in solution. This also shows the arrow proceeding from reactants to products only. And again, that means that this reaction does not run in reverse. Another picture that shows this with the remembering that H plus is the same thing as H3O plus is right here. So in acid, we don't have to show the reaction with water because the proton that is donated comes directly from the acid. If we show water in the formula, and recall that H plus reacts with a water molecule and makes H3O plus almost instantly. So from a former slide, from a former podcast, I said these two are equivalent. So 3 HCl molecules are going to make 3 H3O plus ions, and that is the acidic hydronium ion. From a picture, here's the intact molecule, a little hydrogen and the big chlorine atoms, and then when this is put in solution, we have 3 chloride ions. Chloride's a great spectator, doesn't do anything, and then here are the 3 molecules of H3O plus. Again, a strong acid, no equilibrium is set up. This reaction only proceeds to the right, and it does so in 100% fashion. And the reason I showed this slide with the H3O plus is our weak acid, hydrofluoric acid, only shows the H3O plus instead of the H plus. So a picture of a weak acid, for example, we have 4 molecules or 4 moles of HF. If this is dissolved in water, maybe out of 4 molecules, only one of them breaks apart and makes the H plus and F minus. So this reaction is going to be shown as an equilibrium reaction. And picture-wise, we see that here. Just because there's an H in the formula doesn't mean that 100% of those H's are going to break apart from that molecule. So here are 3, here are the intact HF molecules. So this right here is not acidic. This H3O plus is what makes the solution acidic. An intact molecule is just going to be surrounded by water. It can still be dissolved in water, as we see here from the aqueous state written, but having an H is not what makes a solution acidic. Only when the hydrogen is dissociated from the entire molecule does that make the solution acidic. Okay? So, a weak acid is less than 100% dissociation. And just to recap, the significance of that is we have to look up, our book calls this Ka for acid. We have to look at the equilibrium constant to solve for H+, and more importantly, because this reaction runs in reverse, fluoride will react with water. So we'll talk much more about that when we talk about the pH of a salt solution, or when we look at buffers, and also when we look at a titration reaction. Now the next slide I'm going to show the next paper I'm going to show a strong base versus a weak base. And it's helpful to memorize the strong bases as well. So a strong base, again, means 100% dissociation. And we can pretty much be guaranteed that a strong base is going to have hydroxide in the formula. So our strong bases are always the column 1 metals and the heavier column 2 metals. I don't really think we make bases with rubidium and cesium. I suppose we could. But lithium, remember, column 1 metals are always soluble. So even with hydroxide, which is a polyatomic ion, if hydroxide is with a column 1 metal, that's always going to be soluble. And then the heavier column 2 metals. Magnesium can be paired up with hydroxide, but that's generally a solid. So the strong bases, sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, because calcium is in the +2 column. Calcium, when it is with a nonmetal, is going to lose 2 electrons to the nonmetal. There are going to be 2 hydroxides here. Barium hydroxide would have the same formula. And strontium hydroxide, I suppose we could have listed that one. The weak bases don't have hydroxide in the formula. So again, all of these are completely soluble. So if we looked at the solubility chart, we would see hydroxides are generally insoluble unless they're with a column 1 metal or these heavier column 2 metals. And when we look at sodium hydroxide, I'm going to go ahead and look at that right now, just to remind us that these are going to be an ionic compound, a metal with a nonmetal. So sodium hydroxide, or this could be lithium or any one of these, that's an ionic compound. So remember, we can buy this and it's going to be a solid, as all ionic compounds are. And when we dissolve this in water, what makes this a strong base, again, is 100% dissociation. So 4 sodium hydroxide formula units are going to make 4 OH minus ions in solution. And this is what's going to make the solution basic. Because this reaction proceeds all the way to the right, there's no equilibrium. That means there is no reverse reaction. That's going to be significant when we see sodium in a salt. That means sodium is never going to react to make the intact sodium hydroxide. So sodium is a fantastic spectator ion. It just hangs out and does nothing. It will not affect the pH. So the weak bases don't have hydroxide in the formula, but instead they've got an amine group. So NH3 is ammonia. That's a very common base. base. And bases oftentimes are cleaners. For example, this is lye. So old-fashioned, very strong soap. You can buy ammonia to clean with. So bases are generally real slimy and soapy feeling. But what makes this a good base is the fact that it's got this lone pair on the nitrogen. And what that's going to do is this lone pair will actually react with a water molecule and leave behind an OH minus. So even though there is no hydroxide in the formula, we're going to see that it's going to react with water and make hydroxide. So I'm going to write water as HOH, and then what's going to happen is this lone pair is going to actually pull off this H+. So we'll end up with the ammonium ion in H4+, and that will leave behind OH minus. This is what makes a solution basic. So for a weak base, it's going to be very advisable to always write the water in the reaction. Very it's a little complicated if we didn't do that. And from a previous podcast, I wrote that the definition of a base, I called it a hydroxide donor or a hydroxide maker. And so a base is going to make hydroxide in solution. So a weak base, or a strong base would be more of a hydroxide donor. A weak base is going to make hydroxide by dissociating water. So methylamine, which is CH3NH2, that also has nitrogen with its lone pair. Remember, the formal charge on nitrogen is 0 when it's in this environment. So nitrogen's very happy to have 2 lone pairs and 3 bonds to it. So looking for an N in the formula is going to be something that we're going to want to do if we're not working with a strong base. We want to recognize a base. This would also react with water. And this time I'll write the hydroxide first. It's going to leave behind OH minus, and then this, what's left will be CH3NH3 plus. So as all chemical reactions, we want to make sure that the reaction is balanced atom by atom, and what also needs to balance is the charge. So on this side of the reaction, nothing is charged. Over here we have a -1 and a +1, and so the right-hand side of the reaction also has a net charge of 0. Okay. So recognizing a strong base will be pretty easy because it will have hydroxide in the formula. And a weak base is going to have an N written in the formula. And we'll also see an equilibrium. We should have written that. This also, I should have written both arrows in that direction. This reaction sets up an equilibrium, and again, it prefers to go more to the left than it does to the right. So instead of writing arrows that indicate that, we write an equilibrium constant. So the Kb for ammonia, if we looked in a table, you would see is 1.8 times 10 to the -5th. So that's a pretty small equilibrium value. So when we write the equilibrium constant, if we look at the reaction, ammonia will be dissolved in water, and then we'll have pure water in the solution. This reaction is going to run in reverse, and we'll have OH minus plus NH4 plus. This is also aqueous, dissolved in water, and this is also dissolved in water. Recall from a previous chapter when we write the equilibrium expression for this, we don't include pure liquids or solids in that expression. So this will be our concentration of OH minus times the concentration of the ammonium ion over the concentration of the reactant NH3. And if we set this equal to the equilibrium constant that we are going to get out of the table, then we can solve for OH minus. So we'll leave that for a future podcast.